So which ones should we go over? Most of them. All right, I don't have the worksheet in front of me. I gave them all to Mr. Sam, so I need to steal somebody's. Oh, there we go. I got it one. All right. So which one should we jump into here? Number 1? I thought we did one in class. So we want to do some reaction prediction, right? All right. So let's jump down to number 11. Now, number 11 says solid sodium oxide is added to water. If you see the word solid, that means you leave it together. Now, it's sodium oxide. So you say, well, Mr. Bergman, sodium oxide's in there, so I should split it apart. Well, it only gets split apart if these things are in water. All right, it's going to be added to water, but it isn't in water at the beginning. So it's a solid sodium oxide. So what's the formula of sodium oxide? Na2O. Because sodium has a positive 1 charge and oxide a minus 2. So to balance that out, right? And it's added to water. Now, how do you figure out what you're going to make? Well, if this is all goes back to, actually, if you have your packet, open up to page, what page is that? Like 8, maybe. If you see an oxide, you need to look at the oxide rules on page 8 or 9 or whatever that is. Now, find the oxide. What type of an oxide is sodium oxide? It is a metal oxide. Sodium is a metal, right? This is to the left of the stair step on the periodic table. So what does it say it makes? A base. What base is sodium? What base has sodium in it that you're very familiar with? The answer is NaOH, sort of. Of course, the problem with sodium hydroxide is that it is in there. And now it is in water, so this gets split apart to Na positive and OH negative. Then we go back and we balance it. I believe we need a 2 here and a 2 here. So this is actually the answer right here. So sometimes you write a secondary product and then you figure out what it turns into something else. Yes? Right there, page 9. Okay? Is that clearer now? At least number 11. Let's jump to a couple more. Okay, 12. A solution of sodium sulfide. Sodium, it says a solution, so if it's a solution, that means it's got water around, right? So do we split up sodium sulfide? Yes. So we write that as what? Na positive plus S2 negative. Sulfide is S2 negative. And a solution of something else. Zinc nitrate. Is zinc nitrate, do I split zinc nitrate up? Because it's a nitrate. All nitrates are soluble. So zinc's charge is what? Plus 2 plus nitrate. Now, we now have 4 chemicals that can get together. Usually we try and look first for a precipitate. Are there anything that you could get together that would make a precipitate or an insoluble compound? One that is not a nakelnoso. Zinc sulfide. And the formula of zinc sulfide is what? ZNS. Now, does the sodium, what happens with the sodium and the nitrate? Well, they essentially go like this. Na positive plus NO3 negative. And they cancel. Now, you may cancel it on the, just without looking at it, but that's essentially this right here is the answer. Sulfide plus zinc makes zinc sulfide. And that's already balanced, so we don't have to worry about that. Number 16, excess potassium hydroxide. All right, so 16. Potassium hydroxide. Should I split it apart or leave it together? I should split it apart because it is a Na in the nakelnoso. It's potassium. Potassium hydroxide is added, and it said excess. Let's kind of put a note there. That's important for a moment. To a solution of potassium dihydrogen phosphate. Let's kind of write that out. Let's write it down in the regular. Potassium dihydrogen phosphate. What is dihydrogen phosphate? H2PO4, and the charge of that would be negative. You've got this from your memory list, eventually. So do we split this apart? Again, it's a potassium. Plus potassium dihydrogen phosphate. Now notice we have two potassiums. They're not going to do much with each other, right? Because they're the same chemical, right? So obviously, which chemicals are going to have to get together? The hydroxide and the dihydrogen phosphate. The potassiums are going to just spectate and not do anything. So we've got to think what's going to happen here. What can I make out of this whole deal? Water. You see, whenever you see hydrogens and hydroxides, they make water. All right? So even though there's two H's, we will make, in fact, the fact that they said there was excess means we're going to strip all of the hydrogens off of the H2PO4 minus and make a couple of waters. And then what's the other product? Phosphate, PO4 3 minus. And I think you need to put a 2 here and a 2 here to balance this out. So I mean to rewrite it, it'd be 2OH negative plus H2PO4 minus makes 2 waters and a phosphate. Should we jump back? I heard some concern about number 8. It's got this funny chemical, diamine silver 1 nitrate. All right, it says hydrochloric acid. All right, how do I write hydrochloric acid? You write H positive plus Cl negative. I've seen some people write H2 plus Cl2. That's wrong. If it's HCl is hydrochloric acid. When you split it apart, you split it apart to this. When you write H2, that's when it's in an atom. These are not atoms, these are ions. So hydrochloric acid is a strong acid. If you have a strong acid, you must always make one chemical, H positive, and then whatever else, chloride or sulfate or whatever. All right? And then it reacts with this diamine silver. Now, when we see the word amine, I've helped a number of you on this, amine means ammonia. Kind of makes the sense, right? And diamine means there's 2 ammonias. And you're putting it together with the silver 1 ion. The Roman numeral stands for the charge, right? So this is going to react with Ag. This is just the way we name these complex ions. Diamine, silver, and the charge is +1, nitrate. We'll split off the nitrate because it is, all nitrates are soluble. So now we have 4 things that can get together. And we've got to decide who's going to get together. Usually we look for one thing to happen. This one's a complex one because actually 2 things happen. Now, don't try and make some weird complex thing. Although this is kind of weird and complex, I guess. But I've given you the pattern on how they work. When you're making products, try and make things that you've seen before. So here's hydrogen, and here's ammonia right here. When you put these together, you make a common chemical that you've memorized. You make ammonium. What is the formula of ammonium? NH4 is incorrect. It's NH4 with a charge of +1. So essentially what happens is the hydrogen strips away the ammonia off of the silver. And now what you essentially have left over is the chlorides, and now there's the silver and some nitrate, right? Because we stripped off the ammonia. Now, is there anything else that can be made? You see, this is the issue right here. If Ag can get together with Cl, because you see all chlorides are soluble with the exception of silver, mercury 1, and lead 2. And so this also makes the precipitate, or the insoluble compound, AgCl. The nitrate goes away. So your 2 products are these 2 right here. The nitrate goes away. So maybe I should write this over. H positive plus Cl negative plus Ag, NH32 positive, turns into ammonium and AgCl. Now to balance this, I have 2 ammonias here, so I'll need 2 ammoniums. that gives me some additional hydrogen issues. So if I put a 2 here, I believe that solves my balancing issue. Is that making more sense as you hear me work through the problem? On question 17, by the way, just skip that. That is actually in the second category. I'll have to. Let's jump at 14. Now it says powdered magnesium oxide. What state of matter is something that's powdered? So what's the formula of magnesium oxide? MgO. Now if this helps you, if you want to put a little S there, that helps you. You don't have to put the state of matter, but if you want to, feel free. And it's put it in a, what was it? What are we mixing it with? Carbon dioxide gas. What kind of chemical is magnesium oxide and carbon dioxide? They're both oxides. So if they're oxides, you find the oxide rules on page 9. But in this case, Haley, you're right. We have a metal oxide, magnesium oxide, and a non-metal oxide, carbon dioxide. But there is a rule about when you have a metal oxide and a non-metal oxide, it makes a salt. So we basically have to smoosh these guys together. It makes one product that has Mg, O, and C in it. What do you think it can make? Magnesium carbonate. Yeah, you've got these kind of combined can kind of make carbonate, right? CO3, 2 negative, right? And magnesium has a 2 positive charge. This is not going to be split apart because it is not a Nagelnoso, plus there's no water. That's the answer. Boom. You're going to just smoosh them together. There is a reverse reaction. If you have a salt containing oxygen, it's in that same rule area somewhere on that page, it will break apart into the metal oxide and the non-metal oxide. So if I say, let's heat up sodium sulfate. I'm just going to make one up now. And we heat it up. This is a salt containing oxygen. What's it going to make? A metal oxide and a non-metal oxide. What will be the metal oxide? Na2O. And I think it's sulfur trioxide. It's not going to be. It's not an ion. It's a gas. This would be a solid, and this would be a gas. So if I were to heat this up, either the triangle means you heat it up. So if I heat that sodium sulfate up, I would break apart into this and this. Or for example, what are your bones made out of? Calcium carbonate. Your bones are calcium carbonate, CaCO3. If I took your bone and heated it up, I won't do that, okay? But what happened to a bone if you heated it up? It would turn into CaO, the metal oxide, and the non-metal oxide, carbon dioxide. At a certain temperature. It doesn't happen at room temperature or whatever. It just, that's what happens. So notice this is a salt, calcium carbonate, that contains oxygen. A salt that contains oxygen. But the reverse is true too. This reaction also, so if I said you have a metal oxide and a non-metal oxide, you put them together, they make the salt containing oxygen. So they kind of, this reaction can kind of go both ways, depending on what you're doing. Help? Yes? No? Less than a blank stare now? Just a little bit? Should we do a couple more? And then I want you to, I don't want to do all of them because, how about 22? A solution of ammonium thiocyanate. Ammonium thiocyanate, do I split it or do I leave it together? So I'll write ammonium, which is NH4 positive. What is thiocyanate? SCN negative. By the way, I'm not sure you know this, but whenever you have the prefix thio, T-H-I-O, it always indicates the presence of sulfur. So thiocyanate, thiosulfate, there's always sulfur in there. So see the prefix thio, it's an indication there's sulfur in the compound. Reacts with, what did it react? Iron something. Iron 3 chloride. Do I split it or leave it apart? Split it. So you write Fe 3 positive plus Cl negative. What are we going to make? Now notice we have 4 chemicals. When we have 4 chemicals, the first thing we look for is for a precipitate. Is there something that won't make a precipitate? Huh? The ammonium and the chloride will not make a precipitate because we have a Na and a Col, right? So then we look for the iron to get together with the thiocyanate. But this is not a common thing that makes a precipitate. If you look at your sort of the ones that don't, so it could make something else. What does it do? Yes. Actually, the ligand is, this is actually, the thiocyanate is a ligand. But together, these can get together to make a complex ion. What would be the complex ion? Fe, SCN, 6, because the charge on the iron is +3. So the number of ligands that hook up to the metal is always double of the charge. If it had a +2 charge, it would have been a 4. But since it's +3, we do 6. Now, what will be the charge of this beast? -3 is correct. Now, how in the world did you get that? The iron has a charge of +3, and the thiocyanate is -1, but there are 6 of them, right? So if you add that up, it comes out to -3. You see, you just add them up. Simple algebraic ones. And to balance that, I think we'll need a 6 here. And the chloride goes away, and the ammonium goes away. Helpful? Good? You just have to just wrestle through these. Now you're going, Mr. Bergman, it's easier for me to sit here and watch you do that. I can't do that. It's just going to be a matter, again, I've taught since before you were born this stuff. So I probably know it pretty well. So you need to just get practice. Okay. Let's pull out the podcast notes from last night. Podcast 4.2, I think we called it. I'm going to do it at the end of class, yeah. Are there any questions on this? Oh, you know, a very good question. What is a salt? A salt is an ionic compound. So a salt, good question. What is a salt? It's an ionic compound. Which means what? A metal bonded to a nonmetal. So calcium chloride is a salt. Silver nitrate is a salt. Calcium is a metal, chloride is a nonmetal. Silver is a metal, nitrate is a nonmetal. Actually, there's one that's kind of weird that is also considered, like ammonium nitrate would be considered a salt. That's not a metal bonded to a nonmetal. Actually, technically, it's a cation bonded to an anion. And ammonium is a cation, and nitrate is a anion. Okay? Good question. Get these verbs I use all the time out. Other questions? Yeah.
I'm basically really confused. Do you think you could do the example you left out?
Yeah, that'd be good. So let's turn to that. I don't remember what it was. We skipped one example when we made the podcast. So we have H positive plus Fe 2 positive plus Cr2O7 2 minus makes water plus chromium 3 plus Fe 3 positive. Now, I didn't show you how to balance it yet. That's the next time, right? Did I balance them this time? Oh, okay. Now, first of all, let's do a couple of things here to make sure you understand this. What is it? What does oxidation mean? Leo goes ger. Lose electrons, oxidation, gain electrons, reduction. But that never really works for me because then you have to like figure out where the electrons are. I like to think of reduction as the loss of charge, and oxidation is the gain of charge. So we want to figure out who's got what charge. Let's just identify charges, or what we call oxidation states. What's the oxidation state of hydrogen in this reaction? It's +1, right? What about the iron? +2. All right, what about the oxygen in the dichromate? -2. All right, now what about the chromium in the dichromate? I don't know what it is. I think it's like 7, but let's figure it out. It'd be 2x for the chromium plus -14 equals -2. -2 is the answer here. That's where I got the -2. Where did I get the -14? There's 7 of them times -2. I think X is 6, isn't it? Yeah, right? Each oxygen has a net oxidation number of -2. -2 times 7 is -14. And so X is 6, right? So the charge, or the oxidation number of chromium is +6, right? What's the charge of the hydrogen in the water? +1. And the oxygen in water? -2. Chromium, very easy, +3, right? And the iron is +3. Now, whose charges are changing? Iron is going from +2 to +3. He's doing what? He's oxidizing because his charge is going up. Whose charge is going down? The dichromate, or actually the chromium in the dichromate, is reducing because he's going from +6 down to +3. Right? Does that make sense now? Now, to balance this reaction out, we must write the half reactions, right? And by the things that are changing charges, one oxidizing and then one's reducing. By the way, if this is oxidizing, it's also called the reducing agent, the substance that causes reduction. And if it's reducing, it's called the oxidizing agent, right? Okay, so now let's see if we can balance this. So I will take the Fe2 positive. Now notice something, I think I said this in the podcast. I will try and center this on my page because you build out from the middle. Don't try and left justify it, if you will. Okay? All right, this is very easy to balance. The Fe's are balanced. What's not balanced, though? The charge. So I have to add electrons. Electrons have a negative charge. Which side can I add electrons to? To the product side. And how many electrons do I need? Just one. That's it. We're done. Then we're going to do the dichromate one. So we've got Cr2O7, 2 minus, and it turns into Cr3 positive. Now what's the first thing I have to balance? The chromium. I don't do oxygen and hydrogen until everything else is balanced. So I need to put 2 chromiums here, right? Now the only thing left to balance are oxygens and hydrogens. There's no hydrogens there, but there are oxygens. So how do I balance the oxygens on this left side? I'm going to put 7 waters on this side because I have 7 O's, and that gives me 7 O's out of my 7 waters. That has created a problem, though. What is that problem? I need to put hydrogens on this side. How many hydrogens do I need on that side? I need 14, don't I? H2O. Because I needed to get O's on this side. Now, I have to then balance the charge. So let's see if we can calculate the charge. On the product side, what's the charge? The overall charge. +6. There are 2 of these at +3 each. The water has no charge. On the right side, the charge is what? +12. You have 14 times +1 plus -2 is +12. Which side needs electrons? And how many? You need 6 electrons. So they both have a charge of +6. Now, when we add these up, we have to have the electrons cancel. Is this a basic solution? No, this is not basic because they said, if you look at the question, it has hydrogen in it. So it is not a basic solution. So it's just an acidic one. Okay, so the top one needs to be multiplied by 6 because you want to get the 6 electrons. That makes 6 of these and 6 of these. So now I simply just carry everything down. So it'll be 14H positive plus 6 Fe2 positive plus the dichromate makes 6 Fe3 positives plus the 2, is that 2 or 3? That's a 2. Plus 2 Cr3 positives plus 7 waters. Because if you add oxygens, you would have to add O2s, and O2s have a different charge. The rule is only one thing can go up and one thing can go down.
So because water has oxygen in it, that's how you found it.
That is correct. Better? All right. My goal for you today, what I'd really like to see happen today, is